Thank you for the invitation. It's a great pleasure to be here. So I'm going to tell you about computational rheology in soft matter. But then when I started doing my lecture, I realized that this is very challenging to talk about all computational rheology in soft matter. So instead, I'm going to talk about some aspect or some computational rheological aspect of soft. And since the school is also about biological material, I'm going to also go through some biological systems. So this is basically the outline of my talk. So the first part of my talk, I'm going to address some mechanical behaviors of soft materials and from a phenomenological perspective, or let's say a macroscopic scale. Then I'm going to be talking about the emergence of elasticity in soft material and how can we understand the fact that the system go from a fluid phase toward a solid phase. And then we're going to be talking about the way of modeling the linear and the nonlinear elastic properties. So yesterday we had a talk about yielding and so on. I'm not going to cover this part. I think Luca would talk more about this aspect. And then I'm going to end up by talking about some perspectives in the field. But the main thing that I want you to get from this lecture is the fact that computational techniques might be very important and strong to get insight into the microscopic mechanism that controls the rheological behavior of different kind of systems. All right, so let's start to tell what is rheology. Even though yesterday I think all of you have a sense of what is rheology, but if you go from an etymological point of view, rheology is coming from Greek. So rheo means to flow, logia means study of or science of. So the rheology is the study of the flow and deformation of physical materials and applied stress or strain. So we are all rheologists. We don't know it, but all of you are rheologists. You have always experienced the fact that if you take your ketchup and you want to take whatever get in the bottom, you need to apply some critical force, some critical stress to get it out of the bottle, right? And then with your favorite ketchup now, whatever you have some leftover, you know what kind of force you need to apply in order to not splash the ketchup everywhere. So kids are also very impressive in terms of learning to do rheological experiments. So this is my 2 years old boy, and I took this video just 2 days ago or 3 days ago, and what you can see, he's doing a sheer experiment. He's putting yogurt on the table and splashing it. And this is a way, so people would say, okay, kids are playing with food, but really kids are exploring the mechanical properties of food. I'm trying to get sense of how they could deform it, how they can sense the material or the food that are in their hands. So all of you are rheologists, but we need to go through basic concept to understand fundamentals of rheology. So what is important to understand and why is it important to understand the rheological properties of materials? So the rheology is important for many systems and for many science fields. For example, it's important in geophysics, for catastrophic events like pericrustic flows when you have an eruption, volcano eruptions. It's also important for avalanches to understand why you have avalanches and the way to predict avalanches, but also in earthquakes. So in earthquakes, mainly you have also granular layers in the fault. And this is very important to understand how you initiate an earthquakes and how earthquakes propagate. It's also important for food science and care product, the way to manufacture this system, the way you get nice feeling or taste is related to the way the system or the material deforms as well. It's important for material science from a perspective of durability, but also for carbon footprint. For example, a lot of activity is going around cement paste and the way to improve the rheological behavior of cement paste in order to decrease their footprint, or if you can just replace them. It's also important, and we have example yesterday for 3D printer and the way you exclude the material from the printer in order to build a material. So we want a material that flow, but then instantaneously they got into a solid phase if you want to print something with precision. It's also important for biomedical system, like for implants. So for example, if you take cartilage, you want to design a material that have the same rheological property or mechanical property as cartilage, and that it can sustain multiple loadings. So when you walk, you are just applying a stress on your cartilage, and you don't want the cartilage to degrade. But it's also important for biophysics and medicines, for example, for blood flow, for how cells moves inside extracellular matrix, because they need to sense their environment. So the rheological property of the extracellular matrix and also of the cytoskeleton is very, very important. And it's very important to try to understand some diseases. So for example, here I'm showing a picture of this kind of disease. It's called the syndrome d'Ehlers-Danlos. And it's basically a mutation of some genes of the collagen network. And then the collagen start to be hyperelastic. And you see that your skin start to be really hyperelastic. And this is very problematic. So the rheological property or the rheology is really important in everyday life, but it's almost everywhere. So I'm going to be focusing about soft, what I would say amorphous biomaterials. But what I mean by that is materials that they have as a structure like a liquid, in the sense that there is no long-range translational order like in crystals, but they have the mechanical properties like a solid. And these are some example of these materials. So if you put in this scale the size of the constituent that made the material, you can, in the millimeter size, you can have granular system or suspension. If you go down into scales, you have colloids, where thermal fluctuation now start to be important. It's a picture of a colloidal gel. Also protein gels are formed with protein. They form also a gel. But if you go down into the size of the constituent in the scales and nanometer scales, also in the biopolymer system, this is a picture of this cytoskeleton in cells. And the idea is try to understand how do they switch behavior from a solid towards a liquid and their external stimuli. So let's define what we mean by a liquid and a solid, just some basic mechanical aspect. So if you start with a system of size h and you apply a stress or apply a deformation, delta x, then your strain would be just delta x divided by h. In this case, if you stop, the system would resist and go back to its initial form. The system is elastic. And then the stress is related to the strain with a shear modulus in this case. So keep in mind, this can be generalized as tonsorial form. I'm just talking about just non-tonsorial expression. On the other side, if you have the system that flow, if you apply a stress or deformation, then your shear rate is simply the velocity that you apply divided by the size of your system. And at the same time, the stress would be related to the shear rate with the viscosity of your system. Okay, so let's talk now about some macroscopic phenomenological aspects of this type of materials. So here I'm showing some example of gels. So I'm going to start with carbon black gels. Here you have a nice microscopic picture about these carbon black cells that are suspended in the fluids. They form this interconnected sparse network. And then if you do a startup shear experiment where you apply a stress and you measure or you apply the strain and you measure the stress, you can plot the stress as a function of the strain. And what you see is that you have a fairly linear regime, some nonlinear regime with this two peaks that I think Simon has talked about yesterday, this double yielding, but let's say that the yielding is here, and then the system eventually flow. And this I would call a reversible system, in the sense that if you stop doing your experiment, you wait enough, the system might reform again, and then if you apply again a deformation, you would recover similar curves. So there is no need of external parameter in order to rebuild the connection between your particles. On the other hand, you can have other type of system like casein gels. This is just your yogurt. When you eat your yogurt every day, what you do, if you try to steer it, you would see that this is an irreversible process. When you steer it, when it starts to flow, there is no way to get it back unless you apply an external parameter like pH or, sorry. So this is, again, microscopic image of the network that you have, very similar to that one. You have a sparse network interconnected. This is the size of your units of these protein gels. And here you have also the stress as a function of the strain, and you cover a linear regime. You get some nonlinear regime here where the system is getting stiffer and stiffer, and then eventually it will break, or you have a failure here, a fracture, and then the system you never recover. So this I would call an irreversible system. So here I'm showing a video now of an experiment that has been done in the group of McKinley, where they have used this yogurt and applied the startup shear experiment. Again, the same curve, and then you would see what would happen. So here you would watch in the rheometer your yogurt, and you'd see that the system here is strain stiffening. You don't see much happening. And then at some point, you would start see the nucleation of some fracture here, and then eventually the system will completely fracture. All right. So if I try to see some common aspect between all these materials that have some reversible or irreversible type of interactions, so I can also look into the modulus or the shear modulus by doing a frequent or amplitude sweep, by doing oscillation in my system and changing the amplitude, and then I would measure the modulus as a function of the strain that I would apply. Again, for casein gel, here is the modulus, is not the stress as a function of the strain. So you get a linear regime, and then the system, if you change the volume fraction of the system, get this strain hardening. This strain hardening is also seen in other type of material, like rubber latex, natural rubber latex material, where the modulus also at some point would increase dramatically with the strain, as if the material is trying to resist to the deformation that you apply. And this is a very natural thing that you find in nature, because in nature or in your body doesn't want to break apart. So when you have a situation when you have a lot of stress, your system try to avoid breaking and try to resist to that. So for example, if you look into biopolymer networks like collagen, actin networks, and many other systems, you find basically the same phenomenology. So you have a linear regime, and then you have a nonlinear strain stiffening, where the materials try to resist to that deformation to avoid degradation, because degradation is not very good for your body. So there is some common microscopic phenomenological aspect between all these materials, even though if you look at them from far perspective, you don't see anything in common. What is common between the cytoskeleton, casein gel, rubber, latex, and so on? So here I'm trying to classify all this system in this graph, just to summarize the phenomenology or the macroscopic behavior that you find in nature or experiment. So here I'm plotting the stress as a function of the strain, right? As I said before, for all this system, you would have a linear regime. Then eventually you can get a nonlinear strain stiffening regime. And then after all, the system either would break and you have a failure or fracture, or would flow. And if the system with flow equals that yield stress fluid, you have reversible contact, so you don't need any external parameter to rebuild your network. This is the case for some colloidal gels, for grains, or for emulsions. And in other case, I would call it a soft solid, where now when you break a connection, you're not allowed to form it again. And, and this is the case for biopolymer gels, protein gels like the yogurt, polysaccharides, the cytoskeleton, or the extracellular matrix. And the question that I would try to address here is how, from a computational perspective, one can address how the elasticity arises in all these systems. Is there any physics, common physics, between all these systems in the linear regime, but also in the non-linear regime? So in the rest of the talk, or the first part of the talk, I will talk about physical systems like yogurt, PMMA particles, or cement that have similar structure, even though the interaction between the particles are very different. Yes?
And why should I think of a colloidal gel as a yield stress fluid?
So I think the definition is based on the terminal regime. So if the connection doesn't form and then just start to flow, then for me it's fluid, right? If it's not flowing and it's breaking apart, then nothing happened, and then I call that a soft solid. That's the only distinction. Try to find some common aspect and to distinguish between these two. The only way I found it, but I agree that it's also a solid, but then at some point it starts to flow. So soft yield stress fluid, I don't know how to call it. No, it's yeah, it's based just on the terminology. Okay, so how this system would form. So the, let's say the common wisdom to understand how these gels, or how this sparse network would form, is the following. You have many parameters that you can change in your experiment. For example, you can change the range of the attraction between the particles. You can also change the volume fraction between your particles, right? So thermodynamics will tell you that at equilibrium, you have a phase separating region. You have a region that if you go inside your region, you expect that the system would phase separate in a denser, phase and in a low density phase, right? But then this system, when you put them together and they start to aggregate, the aggregation process, the kinetics is very important. And if you start from a fluid suspension and the system start to aggregate, you enter this regime, then what the system would do is start to form these strands that are connected together to form a network. And then the kinetics start to slow down and the system got stuck into this arrested state that I would call a gel, where you have strands and you have that are connected together and they form a percolating network. So this is like a textbook vision about how to form this system. So here I'm showing a video of an experiment in Tanaka group that they follow the gelation process and how the elasticity emerge. And basically the color that you see is related to the cluster that they are forming. You see the system start as a fluid, and then the particles start to aggregate together, form some cluster, and then at some point the cluster will merge together to percolate over all the system. So these systems are complex in the sense that they are multi-scale materials. So you have different characteristic length scale from a structural point of view. They can be fractal at intermediate length scale. They can have some glassy phase at short length scale, and so on and so forth. So you have different type of length scale that emerge in this system, and that's what make it a little bit complicated to understand why and how the system get into a solid phase and how can we understand the elastic property of this system. So speaking of which, of the elastic property, if you measure now the modulus at vanishing frequency, so just the shear modulus as a function of the volume fraction, your control parameter, for all this system, what you can find is that the shear modulus scales with the volume fraction with some exponent phi. And this exponent doesn't seem to be universal. So if you plot it as a function of the volume fraction, you can get exponent 3, 2, 4, and you can get even more than that. So the mechanical properties also are very complex in the sense that they depend on the interaction between the particles. They depend, as I told you, on the kinetics of gelation. So if you quench your system fast or you do your experiment slow, but also it depends on the particle concentration and so on and so forth. So this makes it a very challenging system to understand. So in the first part of the talk, I will try to understand it, try to convince you or show you that there is a generic scenario for the emergence of the elasticity of this system at low density. And the answer is the following, is that the elasticity emerged from a rigidity percolation transition. And I will define what is a rigidity percolation transition just in the next slide. Okay, so the first kind of model that you can do computationally is lattice models. Lattice models are very simple, but are very powerful, and they have been very powerful in many fields. And the idea is the following. Let's start with a triangular lattice, and then you fill it at some probability to put particles. Or you start by filling it all your lattice, and then you deplete with some probability, right? Then you say, okay, when I have a contact between two particles, so when I have a bond between the particles, the interaction is just a spring between them. And if I don't have any contact, there is no interaction. Very simple model. And then I would try to see how this system behaves once I change the volume fraction in my system. So, but to change the volume fraction, I want to understand from where the rigidity comes from. And for that, I need to define what is rigid and what is not rigid. So what you can do is look at small cluster and ask yourself, does this cluster is rigid or not? And if you look into the literature, this has been well done since a long time ago. And it's also, I mean, in 2D, at least it's a lemma theorem in graph networks. And the idea is to count how many constraints I have in my cluster versus how many degree of freedom I have, right? So I have edges, I have vertices. Each vertices have 2 degrees of freedom, and each edge would add a constraint in my material. So the minimal rigid object in this dimension that you can form is this one, where you have 3 vertices and 3 edges. So if you have more constraint than degree of freedom, then your system or your cluster is rigid. On the other part, if you have a system that have more degree of freedom than constraint, then your system is floppy. You can deform it without any energetic cost. So as I told you before, you have an algorithm, a well-designed algorithm called the bubble game. Doesn't matter the name, but this is a fast algorithm that go through all your cluster and try to identify where is the rigid cluster and where is the floppy cluster. Now let's start with percolation. I start filling my network. At some point, I will find the path that goes from the bottom towards the top or from the right towards the left. And this is what I would call connectivity percolation. This is well established in the field. People have in the critical phenomena literature, people have really understood how the connectivity percolation arises, what are the critical exponents in that, what is the transition, trying to predict them. It's well established. Then if you keep increasing your density, at some point you would see merging some rigid cluster. Here I'm highlighting one of those rigid cluster in this system. But still, this rigid cluster is in a system that percolate, but it's not rigid. It has connectivity percolation in the sense that if you send a current from here, you would have uh, something from the other side, but also if you try to find a path from here to here, you would find a path. Still, your system is not rigid. If you keep going that, at some critical volume fraction, this rigid network will also percolate, and you have a second transition. And this is what I call a rigidity percolation transition. So you can use your model to compute, you can compute just the elastic modulus. And here, what you see, if you compute the bulk or the shear modulus, up to this critical volume fraction, your modulus is 0. And then at some point where the system percolates at this critical volume fraction, you have a finite modulus. So there is a transition. It's a second order phase transition that emerges when all those clusters start to merge together, but they have enough constraint or more constraint than degree of freedom in order to be rigid. And this transition is, as all phase transitions, second order phase transition, are characterized with critical exponents. A critical exponent related to the correlation length, nu, but also to the size, the growth of the size of your cluster, which gives you the fractal dimension. There are hyperscaling relation and so on and so forth. But I want you to keep attention on this exponent u, because this exponent u turns out to be very important in order to predict the emergence of elasticity, but also the linear properties of a system, the linear elastic properties. Just by knowing this exponent, you would be able to trace back what would be the rheological property of the system.
When you talk about elasticity here, you mean shear modulus?
Shear or also bulk modulus.
And you test it, so this curve, this plot there, elastic modulus is a function of P.
Yeah.
You apply a force, and then you check whether or not there is an elastic response.
Yes, a macroscopic elastic.
But this plot does not change if you, for instance, apply a constant force, a time-dependent force, like oscillatory. The details of this.
Yes, I will get to the details of this after. Now just quasi-static, no transient, nothing. But I will talk about viscoelastic properties after. All right, so rigidity percolation is very different, as I told you, from connectivity percolation, in the sense that this is a very no-local problem. So with connectivity percolation, you might be able to break a bond in your system without really breaking a huge amount of your network, without breaking the connectivity in your network. Whereas in rigidity percolation, since the bonds act as a constraint, if you break one bond, you would have a large non-local effect, because you might break a cluster and you form two large clusters that are floppy. For example, if you take this structure, if you break any bonds of this structure, the structure will fall apart and will be floppy. So rigidity percolation is really very different from connectivity percolation, because this is, you have this non-local effect that comes from the constraint that you put in your system. Okay, so we have used this model of putting a lattice model to try to understand how the elasticity would emerge in the system. As I told you, for example, in colloidal gel, also all the other systems, the structure is very heterogeneous. But when the systems start to self-assemble, what happens is that the system will create some frustration, because they are colliding together, forming some small cluster. And this frustration would lead to some structural correlation in your network. So it's as if the system is smart enough to not just form a big blob when it starts to aggregate, but it needs to form, because of the frustration, really some thin structure that looks like bridged-like structure like this one. and these structures are guaranteed to be rigid. So if you use a lattice model and you put some structural correlation in the way that you put your particle in the network, you find out that you recover the phase diagram that I showed you in the beginning, or some aspect of the phase diagram. So you can vary the concentration, you can vary the degree of interaction, and the degree of interaction is tied to increasing or decreasing the interaction is like increasing the correlation in your structural correlation in your network. And with that, you have this phase diagram where that separate two regions. Here you would have a rigid network, and here you would have a floppy network. And as you can see, you can really form, at least in 2D, you can really form a rigid network at relatively small volume fraction. And this is due to the fact that the system self-assemble in this way, where it's smart enough to form this rigid-like structure because of this frustration. This has been recently pointed out also in experiment, also in Tanaka group, where they looked into how the systems start to be solid and try to identify the constraint and the degree of freedom in their system by doing some imaging, confocal imaging. And they end up in conclusion saying that basically when the systems start to be solid, it drives a transition between under-constrained toward an over-constrained system. So rigidity percolation is very, very, very important. Okay, so now you have showed that rigidity or the elasticity emerges from this rigidity percolation. How can you now understand the elastic property? How can you understand the fact that the modulus increases or depend on many parameters, and for instance, increases with the volume fraction with a power law that changes from one system to the other? So to do that, what you can do is to go to more refined models. And I could call this model class of model discrete modeling. I will tell you the general scheme to do this discrete modeling. And the idea is the following. So you start with a box and you put some particles, discrete particles, right? The first thing that you would do, and you will go through these steps afterward, is to initialize the particle position and velocity in your box. Then you need to calculate the force. You need to give some input to know what are the forces between the particles by using some potential energy function. I will go back to that just in the next slide. Then what you would do is to integrate your equation of motion by discretizing your system. You would then update again the position and the velocity, and then repeat this process and loop back also this process. All this discrete modeling, going from molecular dynamics, coarse-grained molecular dynamics, discrete element modeling, and so on, are based on this scheme or this idea. So the first thing that you need is to set up the force and calculate the force. So you need to give some potential energy when you have two particles that get close together. What would be the force between them? And for that, you can use many different kind of forces depending on potential, depending on the system that you are interested in. So for example, if you are interested in emulsions, or if you are interested in granular materials or different kind of system, you can use repulsive potential. So when you have contact between two particles, then the energy starts to increase and you have repulsion between the particles. If you have a colloid, you can use something like a Lennard-Jones kind of potential, where you have repulsion when the particles are very close together, but you have also attraction when they get into contact. You can refine this if you have electrostatic interaction, for example, by adding some electrostatic shoulder. So you have repulsion at these intermediate distances, and then if the particles come really close together, they feel the attraction and they fall into the attraction well. And from that, if you give the potential energy or the potential interaction for your system, then the force is just derived from the gradient of your potential energy, right? So how you discretize your equation of motion, since this is a lecture about computational rheology, the idea is similar for all this kind of computational techniques that I was talking about. So what you do is you solve your second Newton's second law of motion. The sum of the forces equal m times the acceleration. The force comes from any force that you have. You have the force, the conservative force that comes from the potential or the contacts. You can add some forces to model, for example, the effect of the fluid. You can add some active force. You can have some add some external force to drive the particle, and so on and so forth. Then what you do is you can do an explicit discretization scheme where you just write down this second order differential equation by just discretizing your system in time or in space. And then from that, you can integrate to get the velocity and to get the position of the particle, knowing the forces. I'm not going to go into really deep details about what are the bottlenecks of these type of approaches. But for example, for the boundary condition, what you can do is say, okay, I cannot do an infinitely large system, but what I would do a system that is big enough, and then I would do periodic boundary conditions. So when the particles goes from one side, it will cross from the other side. And if it goes up or down, it will come from the other side. There are some advantages of these techniques, but there are also a lot of problems with these techniques. One of the big problems that I will not discuss is the computation of the forces. So as you can see, you have two integration steps. You need to find which particle interact with whom. Imagine that you have a million particles. This is an n squared problem. So how each time step, when you integrate your equation of motion, you need to check twice or a power of 200 or a million of particles. This is computationally not possible. So there are some techniques to really try to increase the efficiency of this of this integration scheme, but they are not at that moment powerful enough that you can really have an infinitely large system. But I'm sure that in the near future, and this is something that I will discuss at the end, some stuff will come from artificial intelligence. All right, so let's start to use this computational scheme to design a prototype of a colloidal gel. So what I would use here is an interaction potential that have this attraction well, and then they have this repulsion. This is a Lennard-Jones kind of potential. And then what I need to specify is my equation of motion. You remember the sum of the forces equal m times the acceleration. Fc here is the conservative force that comes from the derivative of the gradient of my potential that I set. F is something that would explicitly model in the mean field approximation the effect of the fluid in my system. And here is a dissipative force that is proportional to the velocity of the particles times some kind of viscosity. And then you can add some white random noise that would model the thermal fluctuation in my system. So what would happen if I start initializing the particle position and velocity, going through all the scheme that I showed you before, integrate those equation of motion, and then look at the system. So this is two videos. One is the simulation and one is the experiment. And what you see, if I play it again, you start with a fluid phase, the systems start to interact, you quench your system by lowering the temperature, and you see that the systems start to form this strand that percolate, that are not that far, visually at least, from experiment. Although I would insist on the fact that looking by eyes is never good for science, but still from a pedagogical point of view, you see that it's close enough. So let's show that this very simple model is able really to grasp the physics that is behind the elastic property or the rheological property of a lot of soft solids. So to now probe the rheological property, you need to impose some deformation in your system and measure the stress in order to get the models. Here I'm going to describe the way you do it experimentally, numerically. At least in experiment, you go, you have a rheometer, you put your system. There are many problems of doing that, but when your system, your setup is done, bottom, and then the system start to, the rheometer start to apply deformation and you measure the stress. So in experiment we do, or in simulation we do something that is similar. What we do is we start with a box, you apply a small deformation, delta gamma, that it's just delta L divided by the size of your box. What we do basically is we start by applying a very gentle deformation of the order of 1% of the size of the system, right? So very gentle deformation. And this is a fine deformation that it's applied to all the particles. So all the particles will be displaced with this affine deformation that is of the order of 1%. Then once you apply this affine deformation, very, very, very small, you see we always discretize everything in computation. Then you let the system relax for some amount of time by following some dynamics. So here, for example, I will let it relax following this Langevin equation, right? With the fluid force and the dissipative force and the thermal fluctuation. So I apply very gentle deformation, I stop, I let the system relax for some time, and then I apply again a deformation, let it relax for some amount of time, and so on and so forth. How could you define now the shear rate in your system? The shear rate in your system is simply the amount of deformation or step deformation that you have applied divided by the time interval that you have waited for in order for the system to relax. You see, in order to apply just a continuous one, I would just do small steps. And the slope of the curve of these all small steps, small steps will give me the shear rate, right? And the total amount of strain, sorry, this is not the shear rate, but it should be the strain. It is simply the number of steps that I apply times the small deformation that I have applied from the beginning. So if I want to deform my system by 100%, then I need to impose 100 steps of 1% of each. Then you need to take care about a periodic boundary condition. So before we talked about periodic boundary condition in the sense that if you have a particle that crosses the box from here, what you do, you take the position minus the size of the box, and then the particle would be here. But now you are deforming your system. So in order to preserve the shear in different direction, you need to take care about what happened at the boundary. And the idea is it's also simple. It's just if you have a particle that crosses from that direction, what you would do is you put some periodic image of your box in all directions. So in 2D, you have 9 boxes. And then if you have a particle that crosses here, it will not come back exactly at the perpendicular to that, perpendicularly to that position in the other side, but slightly shifted. But the amount of shift that you have is related to the velocity or the strain that you have imposed. So in other words, the velocity of your particles would be just the velocity when it was close to the edge of the box minus L times the shear rate that you apply, and integrate that to get for the position as well, right? So when the particle crosses, it's not going from that side, but it's slightly shift to account for the shear deformation. Okay, now I close the box from the technical aspect, and we go back to the physics. So I told you in the beginning that you have this algorithm that is called the bubble game that counts the number of constraints versus the degree of freedom to probe the rigidity percolation. One thing that I haven't told you is that this algorithm is really exact in 2D, but you don't have any generalization of this algorithm in 3D system. So you're stuck. You cannot use this counting type of, uh, of, uh, algorithm to find your rigid cluster, and you need to come up with a different thing. So the only thing that you can do, we are not smart enough to find, at least for the moment, a smart algorithm to find the rigid cluster. So what we do is we take our system, we form gels at different sizes, and then we take the percolating network and we apply just a gentle deformation in all direction in order to probe if it's rigid or not. This is costly because it's not a binary, let's say, algorithm like the one that I showed you before where you are just counting, because here you need to apply deformation, measure, and see if you have a finite modulus or not. But at least I'm going to show that it's working. So here, what I would do is change the volume fraction of my system and also change the size of my system by changing the number of particles. And what I'm plotting is the shear modulus as a function of the bulk modulus. And what you would see is two populations. One population that it's at very small values where we consider it as fluid, so floppy. So all this network are floppy. You do many realization at different numbers of particles. Some realization would be floppy, some other would be not. So for example, you would have some realization that are floppy here, and then some of them would be in the top right part of the plot, and we call this population rigid, right? You see a clear distinction between these two populations, right?
The floppy ones have not strictly zero moduli for numerical approximations, or how should I think of them? They are.
I think they are.
Have a very weak modulus, but finite, or
no,
what?
I think here we are close to machine precision. So if you are very close to machine precision, then it's zero. So that's why. But just it can be plotted at least to see the two. It's yes, it's zero in the sense it's close to the machine precision. So okay, so you do this game by changing the size of your system, and each time you would form one system, probe its rigidity. Sometimes it would be rigid, sometimes it would be not. And then what you can do is plot the probability or the fraction of your system that are rigid as a function of the volume fraction. And what you would see, you have huge finite size effect. This is a clear sign that you have a phase transition in here. And what you can say is, okay, I have a second order phase transition, which is a rigidity percolation transition. And I can rescale all this curve in a master curve by taking this ansatz, where phi c is the extrapolation of the critical point or the critical volume fraction at which the system starts to be rigid, times the size of my system with the correlation length exponent. So if you do this rescaling, you can get the correlation lengths, and you can get also the critical volume fraction. And it's, you see, by changing the size of your system, it's working pretty well. So you need to benchmark your method, and what you find is that if you measure your new exponent in 2D system, you find 1.3 plus minus 0.1. This is very close to what you're getting lattice models that I showed you in the beginning, which is 1.2, which tells you that your method is clearly accurate in 2D, but also in 3D. So in 3D, we find an exponent of 1. All right. Now you have this exponent. I go back to my original problem again. How to really model or understand the fact that you have this steep increase of the modulus as a function of the volume fraction with the power law that seems to change from one system to the other. So what you can do is to look into the literature and also get inspired by other community like polymer science. And people got excited by these kind of problems in the 80s and the 90s and try to understand from where the rigidity comes from, but also how you model the elastic properties. So the idea is the following. You need to see your system as a heterogeneous system, and you have some correlation length psi. Everything that is inside this correlation length psi is heterogeneous, but beyond this length scale psi, you can envision your system as a homogeneous or elastically homogeneous system, right? Above this psi length scale, you lose all the heterogeneities and your system is homogeneous. So inside this, or below this correlation length, you can see your system as some floppy region or strongly connected region, and they are connected with some weak points that they will call singly connected bonds. What you can do is emphasize what would be the effective bending or stretching modulus that they would get from this trend. And once I know that, I can derive what would be the macroscopic behavior of this system that is composed of many of these blobs, right? So you have a correlation length that I told you before that diverge with this critical exponent. And then if you consider just stretching of your bonds or bending of your strands, you get a modulus that scales with the distance to the critical point with some exponent, or in other words, with your correlation lengths with some exponent. And the exponent depends on this nu, which is the rigidity percolation exponent. If you have a stretching, you have this formula, and you have a bending dominated system, you have this formula. So this tells you that if you start applying a deformation, there is only two modes of deformation that are important in your system. One is just stretching of the bonds, and one is bending of the bonds. But which one is important? I haven't put in my system any bending. I just put Lennard-Jones potential, contacts, they form these strands. There is no bending interaction, nothing that depends on the angle. So if you do measurement, what you find is that actually the bending dominates, even though you don't have put any bending in your system. And at that time, they don't had enough computational power to do extensive numerical simulation. Instead, what they did is lattice model with explicit bending and stretching. And again, even for lattice model, they don't have computational power to get to very large system. So what they do is a very small system, and they get close to the rigidity percolation. And then what they say is that, okay, I have a small system. So if I have a small system, I'm basically of the order of my correlation lengths. So my modulus would scale the same scaling with the size of my system, because the only relevant length scale is the correlation length. And since I have a very small system, then nothing is left. There is no size. The only size that I get is the size of my box. And you see that it works pretty well. We have done it also in the group of Emanuela Delgado by using extensive numerical simulations. Here is a picture of this numerical simulation that shows just the bonds between the particles. Here you have stretching, but you have explicitly put bending in your system. And then also you verify this relation. The modulus scales with the correlation length with some exponent nu that comes from the bending dominated regime. So even though in this system you have put bending and you expect that bending is important, in our system there is no bending at all. But still you can do this game by taking just a small system, changing the size and going towards the critical volume fraction. And what you see is that the modulus scales very well with the system size. And the exponent that you get once you approach your critical point is the one that you expect from the bending dominating. So all the linear elastic property of your system are dominated by this length scale, but also by the bending at the level of your strand. And this is an effective bending that arises from this structure that would form naturally in your system. So how to then compute? I told you about the correlation lengths, but I haven't told you how to compute exactly this correlation length and what is the meaning of this correlation length. So in order to get the sense of this correlation length, what we have done is to go back to what people have done in dense system or in jamming transition. And in jamming transition, what people would do is would apply, for example, a dipole force in the network and measure what would be the response in terms of strain field or displacement, right? And then what you can do is change the structure of your network and see if there is any length scale that emerges from that. So you know from linear elasticity, if you have a system that is homogeneous and linearly elastic, if you apply a dipole force, you know how it should scale, how the displacement should scale far away from this dipole force that you have applied in your system. In particular, in 3D, the square of the displacement field, the far field displacement, was scaled to r to the minus 4. The decay of the displacement field goes as 1 over r to the minus 4. And what you can do is take your gel that is sparse, go in different places, apply these dipole forces, measure the displacement field, and then plot it times the expectation that you get from linear elasticity, right? So here is what you get from linear elasticity. But you see that below you have a length scale where you have a deviation from linear elasticity. And this deviation tells you that you don't recover any more linear elasticity and you are probing the heterogeneities in your system. And this is the way we define this length scale. It's a length scale that it's a measure of the mechanical heterogeneities in some sense of your system. So this is a picture that shows you the size of these blobs, of these heterogeneities. So if you are far away from the critical point, or the rigidity percolation point, so if the system is dense, you see that this length scale is small. And then when you can get closer, this length scale is getting bigger and bigger, which means that your system is getting more and more heterogeneous. So you can measure this length scale, extract this length scale as a function of the distance to these critical points. And in 2D and 3D, it follows what the expectation that you get from the correlation lengths with the exponent that you have measured before. So in 3D, it was 1, and in 2D, it was 1.3. So when we found that, we were happy, but not happy enough because this is something that you cannot do experimentally. It's hard to do experimentally. And as I told you, this length scale dominate the elastic response. This is the one that is important for the elastic response. So what can you do experimentally? You can use this very simple trick. Imagine that you have a picture about your system, and then experimentally you can find the position of your particles. Then what you can do is to put a tracer particle on the backbone of your network and tell it to do a random walk. Okay? Very simple. Computational is not very heavy. You just need to know the position. You put it, it does a random walk. If you have a system that is homogeneous and you have a random walker on it, then it will diffuse right away, right? It's a diffusive particle, it will diffuse. But if you have something that is heterogeneous, you would expect a deviation from diffusive behavior. So the particle needs to really explore many configuration. It will be subdiffused, and then at some point it starts to diffuse. And then what you see, you measure the mean square displacement as a function of time. And you see that if you normalize that by what you expect from the diffusive behavior, that would go as t, then you see that below this length scale, the system is subdiffusive, and then at some point it starts to be diffusive. And again, here you define a length scale by taking the crossover between the subdiffusive regime toward the diffusive regime.
Elasticity, you don't have a length scale, it's just a power law.
Yes, but what you have, so you have a power law in the far field that gets you the linear elasticity, but you have another power law in the closed field that deviate from what you expect from linear elasticity. So in other words, the displacement field square goes as 1 over r to the power of 4. This is for linear elasticity, but you have below that r to the r to the power of -1. So you have a crossover from 1 divided by r to 1 to the power of r to the fourth, and you define this length scale as the crossover between both.
Because of some finite size effect, or
This is because of the heterogeneity. This is because your system is not homogeneous enough to recover linear elasticity. In some sense, below this length scale, linear elasticity breaks down. You can't use linear elasticity, it breaks down. And below this length scale, you can envision your system as a homogeneous system. So again, this is something that you can do experimentally pretty fast if you have the images. And if you do that and you extract this length scale by looking into, so here I'm not telling anything about the elasticity, just about the structure. I just need to know the position. I know the position and I extract this length scale that corresponds to the crossover between the subdiffusive toward the diffusive regime. This is the open symbol. See, it corresponds very well with also with this mechanical length scale that we extract. Yes.
So did you mean numerically, or do you mean you take the images from the experiments and you post-process them somehow?
Exactly. So if you give me images of your experiment, and you are able to say, okay, I have enough resolution like in here to say this is the position of I know the position of the particles, then I can post-process this by adding this tracer particle, putting it in a computer if you want, post-process, and get this length scale.
Image or from a 3D image?
From a 3D image. If you do a 3D experiment from a 3D. Remember, I have showed you in the beginning this video from Tanaka group where in some system you have enough resolution to do that. It's very hard to do this, apply this dipole because, I mean, this is challenging, but just from the structure, if you have good images, you can extract this. And the powerful thing about that is that this length scale that comes only from the structure is exactly the same as the one that you get from the elasticity, and exactly the one that controls the linear elastic property. Again, you might argue that, and people have measured many other length scale, you might argue that I might measure, maybe the important length scale is the size of the pores in my system. Maybe the important length scale is the one that comes from the radial distribution function when the system crossover from something that it's fractal to something that is not fractal. You can measure all this length scale, and you see that all this length scale does not follow what you would expect in order to get the right scaling for your modulus. Okay, now you have extracted this length scale. What you can do is now explore the different relevant parameter in experiment that you do it computationally. So I told you that the way you form your system is important. The interaction between the particles, the nature of the interaction are important, and the volume fraction are important. So now what we're gonna do numerically is to design a catalog of gels. So let's start with Lennard-Jones potential. Now let's add, for example, electrostatic interaction and vary those electrostatic interaction. So if you add let's vary the volume fraction. If you vary the volume fraction, we get also different microstructure. If you vary the way you quench your system, the kinetics of the aggregation process, you would get also different kind of microstructure. And if you vary the strength of the repulsive interaction that comes from the electrostatic interaction, also you would get different length scale. So can we understand the elasticity of this system or rheological property in this system within this framework? And the answer is yes. Now I'm measuring the modulus as a function of this length scale. You see that it works very well in 2D and 3D, provided that it's dominated by the bending. If I I add electrostatic interaction, I would also recover the same scaling, but you see that the curves are parallel. All the curves here are parallel. They do not follow into a master curve, right? And the reason why it does not follow into the master curve is that when you form your system, if you change your preparation protocol, your microstructure is changing. But one important thing is that the size of your strands would change as well. And if I told you that the macroscopic elasticity is dominated by the bending, then the size of the system is the size of the strand is very, very important. Then what you can do is measure what would be the diameter of your strands, and you see if you change the way you form your system, this is by changing the preparation protocol or by changing, adding electrostatic interaction or not, you see that the size of your strands, the radius of your strands will vary a lot. And if you go just to classical textbooks, you know that the effective bending of a strand depends on the diameter to the power of 4 in terms of the modulus. Then what you can do is take all your data. If this is true, you measure A and you divide by A to the power 4. You plot it as a function of this length scale. And what you find is no matter what you do to your system, if you change your preparation protocol, if you change your volume fraction, if you change your interaction potential, they all follow into a master curve. If I have to plot all this curve, for example, as a function of the volume fraction, I would find dependence as a power law, as I told you in the beginning, with different power law. So I would say, no, the physics, maybe it's not the same. But yet, yes, because there is a hidden length scale that control the elastic property. And once you get this length scale, and once you know some property of your rigidity percolation critical point, then everything falls onto a master curve, no matter what you do to your system. Okay, so here I discussed just the linear property. There is no time dependence quasi-static regime. Now I'm going to be focusing about the oscillatory rheology, or let's say the viscoelastic property of the system. So if you look into the literature people have done to explore the viscoelastic property, you do this oscillatory shear, you measure G prime and G double prime as a function of the frequency. You can do it for a carbon gel, for example. This is G prime, this is G double prime. Generic behavior is the following. You might get not a plateau modulus that we were discussing just before, and then you get a dependence as a function of the frequency. This is the same also for your yogurt, to get a frequency dependence of your G prime and G double prime with some power law. This is not very peculiar to non-living system. Also in living system, you get the same generic behavior. This is liver tissues, you get G prime and G double prime fairly constant. Sometimes you have an increase as with the power law. If you go to human dermis as well, you fairly similar behavior. Collagen network exhibit also a power law dependent. So now for the linear viscoelastic property, is there also any common physics behind this? And can we understand all this type of behavior? So what you can do is a more refined model. Now, by taking into account, I told you that the bending, the effective bending is very important. So now what I'm going to do, I'm going to put explicitly this bending in my interaction potential. So this is the model that I would discuss. Is I have, when two particle clouds are nearby, they interact with a Lennard-Jones potential. But when you have a third particle that comes and they stick together, they have some bending resistance or bending rigidity that have this form. Then I do exactly the same thing. I solve my equation of motion by adding now an oscillation. Instead of doing this step, I would do just an oscillation to my system. And I can measure the stress by measuring the various stress, knowing the potential interaction and the distances between the particles. So here is the picture about my simulation. And as you can see, zones that are red are under tension, and the ones that are blue are under compression. You see that our system is also very heterogeneous, even though you have put this effective bending explicitly. And this is due to the fact, as I told you in the beginning, that the aggregation process leads naturally to these heterogeneities. Yes?
So you add to your model, you have a pair potential at first, then you add a third particle force, basically.
Yes.
And would you expect that if you want to make the model more elaborate, you add like multiple particle forces and particles?
I will discuss this if I have time. Yes, I will discuss this after. We can do also like polymeric system, and I will discuss it later.
Okay, so how do you probe the viscoelastic property? And the idea is the following. We discussed that, Simon discussed this yesterday. You apply, for example, a sinusoidal deformation, you get the stress, right? And then you can decompose your stress, the one that is in phase and out of phase, and from that you can get G prime and G double prime. I'm not gonna go into details of getting that. I think in the tutorial we will try to understand this formula, but also compute that for some numerical gel in order to get the elastic and the viscous models. But this type of deformation that you, sinusoidal deformation that you apply has some limitation, in the sense that you need sometimes several cycles in order to get to some steady state. You need to go, if you want to have a wide spectrum in terms of frequency, you need to wait really a long time. And then if there are some microscopic processes that are at time scales that are smaller than this longer time that you need to wait, then you might be in trouble. And also if you have, for example, a living system or not, where you have some aging or gelation that takes place, or living system where you have a fast process in your system, then it's also not desirable because you would be working beyond this time scales. So what you can do is impose another type of deformation. And if you look into nature, nature knows what kind of signal are optimized. So for example, radars use this type of signal. It use a pulse or this modulated signal in terms of frequency to know, to trace back what is in front and behind. But nature do best. For example, for the ecolocalization of bats, they use this kind of signal that is modulated in frequency, but also in amplitude. Dolphins use exactly the same kind of signal. They use an eco signal that it's a signal that it's modulated in amplitude, but also in frequency. And I think you have heard of that, the gravitational waves that have been discovered in 2017, the nature of the strain that has been measured is also something that it's modulated in terms of frequency, but also modulated in terms of amplitude. So why don't we use this kind of signal in order to get the rheological response? The answer is yes. Instead of using just a sinusoidal function, what you can apply is a deformation that it's modulated in frequency, but also in amplitude. You apply this type of deformation, you get the response, and then you can, just in one simulation or one experiment, you can get the full spectrum, the viscoelastic spectrum. So here I'm showing the curves from simulation, G prime and G double prime. The points corresponds to the discrete method where you do a sinusoidal oscillation, you stop, you change your frequency, another oscillation, stop, change your frequency, and so on and so forth. But then if you send this signal that it's modulated in frequency, this is the line that you get here. And you see in one simulation or one experiment, you get the full spectrum. And this is very important because you save a lot of time, at least almost 50 times in terms of simulation, but in experiment as well has been designed in a group of Garrett McKinley, you can save almost 2 orders of magnitude in terms of time. Okay, now we have this fast process of looking at the viscoelastic property. What you can do is what I explained you from the beginning, change the way, the protocol of formation of your system by changing, for example, the quenching time, the concentration of your particle in the system. You would get different microstructure, and then plot, for example, G prime as a function of omega for all these systems. So the red one is the one where you change the volume fraction, and the blue one is the one when you fix the volume fraction and you change the preparation protocol or the kinetics. So here I'm putting G prime, here I'm putting 10 delta, which is just G double prime divided by G prime. And you see that you recover similar similar phenomenology as the one that I showed you in the experiment. But the question is, can we understand where this power law is coming from? The answer is yes, and the way you can do it is that actually you can rescale your modulus and your scale in your frequency such that all your curve that I was showing here will fall into a master curve that is given here, for G prime and G double prime. And if you try to fit this with the model, what you need to have is some ladder model where you put your elements in this way, in a hierarchical way, and you need an infinitely large number of elements in order to fit your system. So by using this type of model, what we can show is that you can get back what would be the frequency dependence of your moduli, and this goes back to your, I think, your question, first question about the time dependence. And you can show that the frequency dependence of the modulus scale again with this critical exponent nu that I showed you before. So again, the critical exponent of the rigidity percolation define the elasticity for the plateau modulus. So there is no frequency, but also for the viscoelastic frequency, it also very, very important. Okay. So maybe in the rest amount of time, I would skip this. I would just talk about now biological system and how can we understand some nonlinear behavior for biological so let's go to biopolymer networks. So here is the video that shows you a cell that it's moving, and you see the brights is the actin that is polymerizing and the depolymerizing. If you start to look into the cytoskeleton, there are many important ingredient, many important polymer inside it. For example, you have microtubules that are stiff polymer. You have intermediate filaments that are very soft. You have also branched actin that is at the front of the cell, and it's given by this branch-like structure. We're going to talk about this one. And you have some biochemical regulator. So when the cell is moving, it needs to sense the environment. And the cell is really also a rheologist in the sense that it's applying deformation, trying to sense, can I go through that way or not? And if I cannot, or I need to go through that way, and I have an obstacle, am I able to push that obstacle? And the cell do it very well, because if you have an obstacle, what the system would do is to stiffen the network at the front in order to push the obstacle. And this is what we're going to try to explain. So here is a microscopic image of this branched actin that you find at the edge of the cell. You see it's very beautiful. It looks like really like a tree-like structure with a well-defined angle at 70 degrees. So people have done experiment on that by taking this branched actin, putting in AFM, and then compressing this branched actin, applying some stress, letting the system self-assemble, and then pushing again to probe the response. So if you do that and you measure the modulus in compression as a function of the stress that you apply, so if the system has been grown under, let's say, normal condition in the sense that it had been grown at low stresses, it has some modulus that it's very small. But then if the system has been grown under hard condition in the sense that it has been grown under large stress, so I apply to my system and let it self-assemble in this very weird environment where I'm applying stresses, and then once it's assembled, then I apply again deformation to probe its response. You see it's stiffened a lot by orders of magnitude. So from where this nonlinear elastic behavior is coming from? So the common wisdom in the literature is the following. Again, if you take a network with vertices and edges, as I told you in the beginning, you need enough constraint and degree of freedom in order to have a stiff network. For example, this one will collapse, right? An important thing that is the coordination number, how many edges I need to attach to my vertices in order to get really rigid structure. And this has been worked out a long time ago, where people have been fascinated about making bridges, right? And the idea is the following: I will add more constraint. If I add more constraint, then I end up with a structure like this one, that it's rigid, but it's dominated by the bending. So here, if I apply a deformation to that bridge, the bridge would bend a little bit. I would not stretch the links. I would firstly bend the links. This is a bending dominated elasticity. If I keep increasing the coordination number or adding more bars, then I end up with an over-constrained situation where now if I apply a deformation, I'm not able to first bend the bars, but rather I would stretch the bars between my vertices. And this is a stretching dominated elasticity. So you can do your favorite model on lattice. You take, for example, triangular lattice. You put your springs, and then you put bending between your springs and stretching as well. And you vary the coordination number by depleting more or less numbers of your of bonds. So if you vary the coordination number and you measure the elastic modulus, indeed you find that there is a well-defined transition at some critical coordination number where the system starts to be rigid, but it's dominated by the bending. And then you have a second one where here you have a stretching that start to be dominate. Now, if you take your tree-like structure for the branched-like actin, and you count how many constraints you have, what is the average coordination number that you get for this structure, you realize that your branch actin falls exactly at that point, which means within this framework, I expect that if I apply a deformation to this branch structure, I expect it to be floppy. So from where this nonlinear elastic behavior is coming from? Well, to do that, one can do experiment first to probe the macroscopic behavior. Now, our colleagues at the ASPCI have done that. The idea is to take this paramagnetic beads or rods to grow your branched actin in between the rods, right? Here is a movie that shows when the branched actin is about to grow, it pushes apart the rods, right? And since it's a paramagnetic bead, you can apply a magnetic field in order to compress now the beads. So if you compress them, you know by how much amount you have compressed, because this is proportional to your magnetic field. You can image your system and you can get the deformation. Small rheological experiment, micrometer size. So this is a type of magnetic field that you apply. You apply a small magnetic field where you let the system self-assemble. This corresponds to that video. And then at some point, you increase your magnetic field in order to probe the response, and you decrease it. So if you do that, you can measure the modulus as a function of the stress, derivative of the stress strain curve. And what you see is that you have this really huge strain stiffening by an order of magnitude. So the gel gets stiffer, or the branched actin gets stiffer and stiffer where you apply the stress. And it seems that when you get to very small stresses, it goes to the vanishing modulus. That would correspond to the fact that, as I told you before, the branched actin is right at the edge of being solid or not. Okay, from where the elasticity or the nonlinear behavior is coming from? And the answer is the following. The nonlinear behavior is coming from the fact when you compress your branched actin, you are creating more and more contacts. Okay, you can make this assumption, but then it's very hard to explore experimentally. How would you do that? Well, you can't. So that's why computational rheology or computation is very important. If you can't do it experimentally, you go back and then you design a generic model with enough ingredient in order to simulate branch acting. You compress it, and you verify if this hypothesis is true or not. So this is what we have done. This goes back to your question, I guess, how we form a branched actin. It's the same scheme that general scheme that I showed you before. What I need to tell is just the interaction between the particles. But here, on top of that, I will link the particle together by bonds. I will not let them self-assemble the way they want to self-assemble, because I want this branched-like structure. So I start from a branched-like structure, and then I put links between the particles. So this is the resting state. If I move the particle together and stretch these links, this is very costly, very expensive. I have some bending rigidity. I have a filament with some bending rigidity. If I bend it, it costs energetically, and the cost is proportional to the angle that I will form, or the deflection. And also they cannot interpenetrate. If I have two filaments that comes together, then I put a repulsive force between them, and then they will not interpenetrate. This is a video or a picture from experiment. You see that you have these branches that we designed, made by several particles that are attached together. Okay, how can we do the step compression? Is the same as the step shear. I will go very fast on that. We apply a step deformation, let the system relax with some dynamics, then measure the stresses. This is a video that shows you the compressive and the tensile stress when you are applying a deformation on your branched actin network, and you see that the system has more compressive stresses than tensile stress. Okay, can we prove that the mechanism behind the stiffening in that network is coming from the contact? And the answer is yes. So you can do pretty much whatever you want in simulation. One thing that you can do is to make a simulation where you apply this deformation, measure the stress as a function of the strain, with steric interaction, in the sense that if you have two filaments that try to cross each other, they cannot. But then you can turn off this steric interaction. And if the contact matter, then you would see a huge difference between both. So this is the two curves. This is stress as a function of the strain. This is with the steric interaction. But now if you turn off the contact interaction, you see that the stresses decreases, doesn't change much, which means that if I translate that in terms of modulus, which is the derivative, then if I have repulsive interaction, I have a clear increase strain stiffening. But if I don't have steric interaction, the modulus would be just at 0. This is a proof, and you can do it experimentally, that comes from simulation. Tells you that really the contacts that forms are very important, and you can show it numerically. Okay, now how can we model the strain stiffening? You go back also to the literature, and I would emphasize that literature is very important, and people have done a lot of things that we are not aware about. But for example, I would here put some measurement of the elastic modulus as a function of the stress by doing this compression. I'm not doing shear, compression. This is my branched actin network. But let's see what other networks in the literature do. So if you take measurement from all this filamentous-like network, going from cotton, cellulose, fibrin network, carbon nanotubes, sheep, wool, what you would find is that it seems to fall onto a master curve. Even though the scales are extremely different, the only analogy between these is that they have this filamentous structure. So this tells you that maybe there are some common, again, physics from all this different scale between the branched actin at the nanoscale, but also your hair or the cheap wool when you compress it. And the answer is yes. So to model that, Van Wyck in the 40s was very interested into compressing cheap wool and try to understand how the stress is increasing when you compress the cheap wool. Well, maybe you can say, okay, maybe this is useless. But you see, it's very, very important. Actually, the physics that is behind is very important. The idea is very simple, is to say that I take a ghost filament in a box, I compress it, and then I count how many contacts I have between the filament that forms. If I have 2 contacts that forms, when I compress it, I have an energetically cost due to the bending of the filament. Within this ingredient, what you find that is the stresses goes with 1 over the volume to the power of 3. Very simple mean field model, just counting the contacts in a ghost filament. If you do that, this is what you find in your experiment, but also that the theory works very well and fall on the experiment. So this tells you that the physics behind the shear pole compression is the same than the one behind the branched actin nonlinear elasticity. I think I'm going ahead of time. I'm going to skip this and go to maybe the last plot that is very important. So as I told you, the contacts are very important in this system. And what you can show is really by changing your preparation protocol, by putting your system under stress, letting self-assemble, the system what it would do, or the cell what it would do, is to create more and more contact in order to be stiffer if it tries to push on obstacle. And the physics is the same if you can do it by creating this interlocked contact, but you can create it by putting some crosslinks. So the cell has also the ability to add crosslinks. So what you can do in simulation is do the same thing by generating some configuration with some pre-contact and generating some configuration with some amount of crosslinks. And if you measure the modulus as a function of the fraction of contact, you see that they all fall on this master curve. And the line here is the prediction from some kind of model that is just a slight change of the chi pole theory. So the take-home message from that is that when the filaments are in good state, they have enough space, they are fluid, they don't need to interact with each other, they are at the edge of being solid. But then when you add compression on them, they need to support each other. The cell needs that a lot in order to push on obstacles. And this is by creating contact, permanent contact by adding crosslink, or non-permanent contact by just steric interaction between the filaments. Okay, let's go to the conclusion very fast and perspective. So here, as I told you, rigidity percolation for the elasticity of this soft system is very important. By knowing what happened at the critical point, you can really predict the physics or predict the rheological properties, and also in the linear regime, but also the viscoelastic properties. And all of them depends only what happened at the critical point. Critical point is important. It's like the cosmic wave background, what happened at the cosmic wave background, and the property of the cosmic wave background impact a lot what happened nowadays. That's the same for the rheology for this system. What happened at the percolation, the rigidity percolation threshold, is crucial to understand the linear and nonlinear behavior. So also, I hope that they got the fact that computational methods are very important in order to get the microscopic mechanism that are behind some rheological properties. Some perspective are about the plastic response now. What happens if I break my system or get close to the failure in my system? Can I get some indication or can I really predict what happened at the failure point just by knowing what happened at the rigidity percolation point? What about, and this is something that has been discussed yesterday a little bit, the ductile to brittle transition, when the system is sometimes is ductile, the system sometimes is brittle. How can we understand within this framework the ductile to brittle transition? And one big challenge, I guess, for computational rheology is, as I told you, the bottleneck of this method is the computation of the forces. So can we use neural networks in order to accelerate the computational response of your system by inferring what would be the forces between the network without doing any integration? This would be very powerful in order to scale up this simulation in order to get very, very, very large system. With that, I will just thank my collaborator and student that are behind all this, some of this work. And thank you very much, and take your question if you have.